So today we will start talking about linear equations. And we will talk about existence and uniqueness of the solution for linear equation system. The general form is Ax is equal to B, where A belongs to R m by n, and B belongs to R m by k. Now there is a theorem which you can prove it. Well, the proof is pretty straightforward by using the previous theorems of previous chapters. And it says, consider the following linear equation system where B is not a matrix but is a column vector. Now, there are 6 terms that we have to write. If you remember when we were talking about the range of A, we said that for such system, the solution exists if and only if B belongs to range of A. And there exists solution for all B's which are in Rn if and only if there exists solution for all B's in Rm if and only if range of A is whole Rn. What does it mean? Range of A is whole Rm. Do you remember? What does it represent? This means A is on 2. This also means rank of matrix AB is equal to the rank of A itself. So these two were talking about the existence of this solution. The solution is unique if and only if null space of A is equal to 0. What does it mean? Null space of A is equal to 0. It means range of A is the Rn, it means if A is onto. Null space of A is 0, it means exactly. It means A is 1 to 1. We remember like 2 weeks ago when we were talking about this 1 to 1 and onto, we said if null space is 0, it means A is 1 to 1. There exists a unique solution if and only if A is non-singular but this is a unique solution for all values of B's belonging to Rn. You know what does it mean? This means what was the condition? Do you remember what was the condition for Ax is equal to B to have a unique solution? Something that you have seen in high school in the undergraduate algebra. R is a square and the determinant of A is not 0. A is non-singular. This is like the easy case that we always talk in the undergraduate level. Again, this means A has no 0 singular values. We know that if we have a 0 singular value in the SVD, if we have a 0 singular value, then we will not be non-singular. There are 2 more, but the proof of each of them, if you refer to the book tells you that previous theorems of previous chapters can help you in order to prove each of these theorems. We don't care about the proofs. We need them because later we use them to prove some other theorems. If there exists at most one solution for all B's. What do you mean at most one solution?
More than one.
At most one means that we have either no solution, or if there is a solution, it's a unique solution. Remember, we can sometimes have solution, but it's not a unique solution. Today, we will learn that in general, we have a unique solution plus lots of arbitrary terms. What? Only one solution if it's unique. But here it says that either you have no solution, or if you have a solution, it's a unique solution. There is at most one solution for all B's if and only if the columns of A are linearly equal to 0. Null space of A equal to 0 means 1 to 1. And what is the size of A? It's M by N. It's an M by N matrix. And we have not the column. We have all the columns are linearly independent. What can we understand from this sentence? Columns are linearly independent. What can we comment about M and N? No.
Rank is M.
We understand that M is greater equal than N. Why? Why? But then how do I conclude that M is greater equal than N? I'm saying that they are all synonym of each other. I said what?
One solution, so we can show that
I'm telling you that it means we have that we have all the columns are linearly independent. All columns linearly independent means M should be greater or equal than N. Why? What is rank of A? It's minimum of N and M, right? What is rank of A? Definition. What is rank of A?
Minimum number of independent columns.
Number of independent columns. And as we said that all the columns are linearly independent, so this should be N. In other words, minimum of N and M should be N, which means that M should be always greater or equal than N. They are synonym of each other. It means that the null space of A should be 0. It means that all the columns of A are linearly independent. And the sixth is there exists a non-trivial solution to the homogeneous system. Two questions. Question one, what is homogeneous system? Homogeneous system means A, x is equal to 0. Okay, we equate it to 0, it means it's homogeneous. What do we mean by non-trivial solution? What is a trivial solution to this? x0. x0 is a trivial solution. So we have a non-trivial solution for the homogeneous system if and only if rank of A is less than n. Sorry, n. Number of columns. Now we have, so this first theorem has 6 parts. As I said, they prove, as you can see, are very long into the previous sections, theorems. But now we have 2 important theorems. The first theorem is about the existence of the solution. The second theorem is the uniqueness of this solution. So let's look at these theorems. Theorem, I call it the existence theorem. The matrix linear equation, which is of this form, Ax is equal to B, where we have A belongs to R m by n, B belongs to R m by k. As a solution, if and only if range of B is a subspace of range of F. In other words, we have a solution if and only if A plus B is equal to B. Please read the proof from page. That's a very easy proof. Okay, it doesn't have the proof in the book, but I have the proof in my notes. That's a very easy proof. Suppose, now, do you know what is the meaning of if and only if? Both ways. So first we have to start from one way to go to the end, then we have to do it from the end to the front. So let's start by supposing that we have this term is true. We have this term is true. So let's take an arbitrary vector x belonging to Rk, which means that the Bx belongs to range of B, which is a subset of range of A. This means that Bx is a subset of range of A. This means that there exists y belonging to Rn such that Ay is equal to Bx. I can multiply both sides. No, I don't need to multiply anything. Here I can replace B with the AA plus B. So Bx, which is equal to Ay, is equal to actually A plus Ay. Why? What is the result of this one? Do you remember? Was it property 1 of pseudo inverse? it? A. Right? Now, Suman, what is this?
BX.
It's Bx. It's Bx. So I can write Bx is equal to A plus Bx. Because X is any arbitrary vector, it can be an identity vector, then what do we get as a conclusion? B is equal to A plus B. So if range of B is a subset of range of A, we got this conclusion. Sorry? A plus is like identity because identity multiplied by B is B. Well, we know that this is an approximation. Now, let's assume this is true and get the other part. I keep the theorem. Let's assume B is A plus B, and take arbitrary vector Y, which is in range of B. Then there exists a vector X in our case such that, look, A belongs to range of B, so it means that there is a B X is equal to Y because Y is in the range of B. Upon, and we already know that what is B? A plus B. So Y is equal to Bx is equal to A plus Bx. So Y was in RB. Can you tell me that? Can I write this one as a new term and say that, okay, it's something that A is operating on it, so it belongs to range of A. And the proof is complete. So I use this, I said let's take an element in RB, and I show that that element is also in RA. From this existent theorem, we can actually get a very general form, which is very important. For A belonging to R m by n, and B belongs to m by k, suppose that we have A plus B is equal to B. What do we understand as I said, suppose that this? It means we have a solution. Then any matrix of this form is a solution. Which form? X is equal to A plus B plus I minus a plus a y, where y belongs to R and by k is arbitrary. So, the existence theorem tells me that if range B is a subset of range A, in other words, if B is equal to A plus B, I have a solution. And here is the solution. Solution is A plus B plus I minus A plus A multiplied by Y. Y is any arbitrary matrix that I have. So this means that if I have a solution, my solution is a combination of two parts. One part is unique part plus the arbitrary part, because Y is arbitrary. So we have to open a bit more. Because when we say that we have a solution, we have to show that what the solution is. So this is a solution of Ax is equal to B, right? How can I prove it? I tell you that this is the solution of this one. How can we prove it? Look, I have a simple equation. 2x minus 2 is equal to 0. And I tell you that x is equal to 1 to the solution. How can we prove it? What? No, in order to prove it, you don't need to solve it.
Put x.
Yes, we put x into here, and we say 2 multiplied by 1 minus 2 is equal to 0. So it is a solution. Now, how can I understand that this is the solution to this one? I put x this one. So I should say that Ax is equal to B. So A multiplied by A plus B plus I minus A plus A y is equal to A plus B plus A minus A plus, A multiplied A plus A y. This is equal to, can you tell me that what is the term in parentheses? What is this? A. So it is 0, they cancel each other, so what is left is A plus B. What is A plus B? This is a solution. This is the solution. And this is always a solution. Let's get back to undergraduate calculus. Note, if A is a square non-singular matrix, can you tell me that what is A plus? If this is like a high school very nice friendly matrix, the pseudo inverse will be A inverse. And so solution, we know that for A, Ax is equal to B. What is the solution in general? If it is very good, the square non-singular, it's x is equal to A inverse B, right? So let's see. X is equal to A inverse B plus I minus A inverse multiplied by A y. What is A inverse multiplied by A? It's I minus I is 0, this term is 0. So x is A inverse B, which is unique. We don't have an arbitrary part. So you see, this is the general case, and this is very specific and a special case, and it is also valid. Now, so the previous theorem was about existence. The next theorem uniqueness. Then solution of the solution of the matrix linear equation is unique if and only if, okay, let's see what is the condition. What was the general solution? A plus b plus I minus a plus a y, right? And we said it is a combination of two parts. What are the two parts? This is the unique. This is the arbitrary. Now, what is the condition to have this one to be unique? So how can I make sure there is no arbitrary part? What's the condition not to have an arbitrary part? Sorry?
A pseudo result A is
Very good. If A plus A is equal to I, then it will be I minus I, then the arbitrary part will go away. Okay, what does it mean? A pseudo inverse of A is equal to I. It means null space of A is equal to 0. It means null space of A is equal to what is the side? A belongs to R n by n. What is the meaning of this one? It means A is 1 to 1. A is 1 to 1. Let's do one example. Suppose A is a square. Find all solutions of the homogeneous system of Ax is equal to 0. Guys, look at it for a second. But the solution is this. X is equal to A plus B plus whatever. So it is x is equal to a plus, what is b? 0 plus I minus a plus a y. This is 0, right? So it means x is equal to I minus a plus a multiplied by y, and we know that y is arbitrary matrix. So we have non-zero solution, we have non-trivial solution if and only if, under which condition we have non-trivial solution. Look, this means non-trivial solution. Under which condition I have this? What is the condition that tells me that, sorry, you have only trivial solution? What should be the condition not to have this one? If and only if a plus a is not I. Now, when do I have, for this example, now I'm talking about only this example, when do I have in this example a plus a not to be I? This means a is singular. That I have pseudo inverse because we know it's already a square. In order to keep it in the pseudo form, it should be singular, or it means rank of A. What should be the rank of A? What should be the rank of A for this example in order to have non-zero solution? If it is n, then it means that it's singular, it's not singular, and I have A inverse, and I'm doomed. So it should be less than n. There are two examples in our book, example 6.9 and 6.10. They are talking about reachability, controllability, reconstructability, and also the observability for control systems. We don't talk about those examples. If you are interested in control systems, you might look at those examples, but you are not responsible for them. Now, we have another theorem. The consequence of this theorem is important. Let A be R n by n, B be n by q, C be P by q, then the equation A x C is equal to B has a solution if and only if A plus B, C plus C is equal to B. And in that case, which means if we have this condition and we have a solution, the general solution will be a plus b c plus y minus a plus a y c c plus y is in matrix of n by p is an arbitrary matrix. So you can see that this is more general theorem. Why is it more general theorem? Because in previous case we had A is I is equal to B, right? And if I do so, then it means that X is A plus B I plus Y minus A plus A Y I plus. I know that these are 1, this is 1, so it will be A plus B plus, I factorize Y, so it will be I minus A plus A Y. So I get the previous case. If you remember in chapter 1, you have done homework of that chapter also, we have inverse of matrices, and there was some block matrix. Do you remember? We had block matrices. I think I even assigned you homework. You're supposed to do that one. Now, I want to write them again to remind you a few important inverses. You don't need to prove them, but maybe when you are doing some of the homeworks or in the exam, you can use them directly. Okay? They are all available in our book. Assume that the sizes are matched. So in all cases, let's assume that we have A belongs to R n by n, B belongs to n by n.
Why we need to the block matrices in this proper contractility and
Sorry?
why we need to the block matrices in this?
No, you're finished. Consider these block matrices, we want to write some inverses. Because sometimes when you want to calculate the inverse, it's easier to divide them into several blocks and apply the blocks inverses. Look, actually many algorithms that we have for calculating the inverse, like if you have to have a big matrix, it doesn't calculate the inverse in general. What it does, it divides into the block and it applies these block formulas, because then you might have here a 2 by 2, here you might have another 2 by 2, so instead of 4 by 4 you can have these 2 by 2s matrices that you can calculate the inverse. The first one, which is new, you have not seen it, the other ones you have seen them, is called Sherman, Morrison, Woodbury formula, and it says A plus BDC inverse is A inverse minus A inverse B, D inverse plus C A inverse B inverse C A inverse. The second one, inverse of whose identity, whose diagonal is identity matrix would be itself, except this plot is negative. But if one of them is minus I, we will get the same thing. Minus A inverse B, D inverse. You remember that from the first chapter. You can see that these 2 is the number 4 is general form of 2, and number 5 is general form of 3. Because if you press I and D with the I, you can get the same thing. If you have A, C, B, D, the full block inverse, that E is equal to, do you remember what was the name of this term? It was called score complement. The same inverse can be calculated by score complement of D. So A is the same matrix. And F is score complement of 3. Now, before we finish this chapter, okay, these are the things that no one expects you to memorize. They prove some of them, you already have proved them. But it's always very handy if you need them in order to write, let's say, a computer program to calculate something, or if you really need to calculate some block matrices by using pen and paper. Now, we will talk about something which is not in our book, but it's playing a very important role in computer science. in general, if we have Ax is equal to B, we solve the system, of course, after we see that the solution exists, by using several well-known techniques. Lower upper factorization or decomposition, Cholesky factorization, QR factorization, and singular value decomposition. You can use them in order to solve it. However, you want to focus a little bit on some aspects of the first two. In the AU decomposition or factorization, what we do is this. We say that AX is equal to B. We apply LU decomposition, so we get LUX is equal to B. So I can write it as LY is equal to B, so I can find the value for Y, and then I can equate it to this one. Do you know what is the lower triangular, what is the upper triangular? Lower triangular matrix is this, and upper triangular matrix is in this form. So it's easy to manipulate because here I have only one coefficient. I can easily calculate what is the first one. Now, I have two sets of equations. First is Ly is equal to B. The other one is Y is equal to Ux. The total number of operations for AU factorization is about 2 over 3 n cubed. And solving the S star equation is 2n squared. Total number of operations will be 2 over 3 n squared plus 2 over 3 n cubed plus 2n squared flux. Cholesky decomposition or factorization says this. Ax is equal to B, then I can write L transpose X is equal to B. But here, A must be positive definite. We will describe what it is in a few seconds. But then, it means that I can write here y is equal to B, and then say that L transpose X is equal to Y. So I have two sets of equations. Now, look, in any decomposition, I have to calculate L and U. But in here, I have to calculate only L because the other one is L transpose. So, total number of operations for what is the total number of operations for calculating the Cholesky decomposition? If this is 2 over 3 n cubed, how much is this one? 1 over 3 n cubed, because it's half of it. I don't need to calculate u. So it will be 1 over 3 n cubed plus this part is the same, 2n squared. Now, why do I need to talk about this one? Because in computer science, when you are developing an algorithm, you need to talk sometimes about the flops. Which one do we prefer? This one or this one? This one, because it has less number of flops. But sometimes I tell you that, boy, you cannot use this one, you have to go and use this. Why? What's the problem here? A must be positive and definite. So let's see what is a positive definite. A is positive definite if it is symmetric and for any x transpose A x, it has to be greater than 0 if x is not 0. X transpose A x is 0 if x is equal to 0. So in this case, we call it is positive definite. A is positive semi-definite if it is symmetric and okay, can you tell me what is the condition? Definitely x transpose A x is equal to 0 if x is equal to 0. What about here? When x is not equal to 0, what is the condition in here? For positive semi-definite. It will be greater equal than 0. In other words, there are some terms which makes this result 0, but x is not 0. Then in that case, we call it semi-definite, positive semi-definite. But we understand Cholesky factorization is valid if we have a positive definite. I give you a question, a very, very simple question. And I will solve it on the next lecture. And the question is this, example. Please remind me I start by solving this one. Which, or let's do this one. Investigate the positive definite or semi-definiteness of these two matrices 9, 6, 6, 5 and 9, 6, 6, 4. For next homework, of chapter 6, question 236. So for these two, you have to check if they are positive definite or positive semi-definite or none of them. What do you mean none of them? It means that there is a possibility to have x transpose A, x to be negative, but it's not positive definite percentage. Now, next lecture, I will talk about the projection norm and inner product of the matrices before we go and talk about the IMI